are like the prompt engineer. They just try type different. So they have a new title. I'm a prompt engineer, but they don't know how it works. Okay, so. But it's very interesting if you are the type mathematicians or whatever philosopher, like Stephen Wolfram, I talked about. You want to know how it works, okay? So for a programmer, if you are already a programmer, or if you are engineer or mathematician, so you can study how it works. It's a field by itself. So you need linear algebra, you need some calculus, then you can, it takes a year to really understand. So I'm kind of doing that. Okay, and especially, in my past few videos, I talked about proof theories, like the Lean programming language. So I'm also learning that. So they work together great, because neural networks, by definition, by its nature, they are never precise. Like, they cannot solve math problems. If you ask what is a plus b, where a and b are like 20-digit number, they got wrong. Okay, we showed this many times. So for example, let's say a random number. Okay, random number. Okay, let's say times. Okay, can we run this, save this in let's say Python. Okay, Python print that, is it big enough? Okay, so that times that. Okay, now ask ChatGPT, okay, what is, okay, he'll get it wrong. Assign the first number, second number, perform the multiplication, result is that. Usually it gets wrong, but I think today it gets right, because it actually calls Python. Let's see. No, it's wrong. You see, this is the correct result. Okay. Quark result. Okay, this is the correct result. This is a quark result. Okay. Incorrect. Idiotic. Totally wrong. So you can fix that. It's just wrong. Whenever you need some simple computation, the seemingly advanced AI bots, they will always get it wrong, because this is very interesting and fundamental, because they cannot compute. Okay, it seems like they are so smart. They can write poems, they can answer difficult questions, they can tell you what are the theories of math, but they cannot compute simple calculation. They cannot do. So in order to, that is the nature of neural network. Okay, they cannot do it. That's it. There's no fix. Okay, the llama bots, they just cannot. Okay, that's a fundamental nature of neural network. That's why it's called machine learning. They don't actually compute. So a lot of people tries to fix it. One way is to have proof system, Lean. So when you came out the result, you validate the result. For example, when you determine, when the chatbot determines it's kind of like a math question, they can feed it to Python. They just launch Python and just do print. Then they'll tell you the correct answer. So that's how the Lean proof system can help. Anyway, that's it for today. Thank you guys for watching. No comments. People watching us. Anything else? Okay, that's it. Random let's clean up and shut down. Place the Python. So press a programming degree. No, I'm uncertified, and I'm kind of self-taught for reasons. Okay, because I wasn't normal. I don't have a normal background. Okay, so this what is T made of? Okay, let's open a new window and let's do a screenshot of it. Anyway, that's it. Bye. So pay me, okay? Go to PayPal. Go to Sali.info. And go all the way to the bottom. Go back. So I want to do something. It's okay. Let's make the screenshot there. There we have the result of the herbal tea. What's herbal tea screenshot? And what is tea made of? Okay. And change it to underscore. Copy the file path. Close it. Paste the link it. Paste. Show in browser. What is tea made of? Fantastic. So we have a record of it. And what is this origin of herbal? Okay. New buffer, paste text. Okay. Copy the file path, close. Okay, wait. We want to replace space by underscore, rename. Okay, there it is. Copy, close. What is Emacs shell? Okay, we don't care about that. Go back here. Where is our... Open that and link list. What is the origin of herbal tea? Okay, what else? What is ChatGPT? No thinking. Okay, so that's another question. It keeps thinking because you cannot remove that, as we learned. Very interesting. You cannot remove the thinking in DeepSeek. It needs to think. you know, hey, answer me this question, but do not think. Okay, so it just it needs to think. Okay, what is this? Okay, so close that Python we don't need. Go to the talk show. And here's the question we ask: what is ChatGPT? No thinking, but it thinks anyway. Then Grok told you that, DeepSeek has to think. You cannot tell it not to think because it's part of it. Okay, bye guys, shut down. Yellow, hi every.
I recently learned about the Andromeda paradox, a real effect in Einstein's relativity. I didn't understand it, and that really annoyed me. Let me play you the clip that confused me so much. It's from a recent Star Talk episode with astrophysicist Hakeem Oluseyi.
What is the Andromeda paradox?
Well, the Andromeda paradox is the fact that if you and I are looking at Andromeda 2.5 million light years away, then what happens is, suppose you're sitting in your chair and I'm running by, and at the second I run by you, we both look up at Andromeda. Because I'm moving and you're stationary, we're going to see events that are days apart, even though we're in the same location looking at the same time.
How can that be?
You think that relativity, and you think that the
Don't just
light
say relativity and keep talking.
How
I know,
far?
right?
Wait, in this scenario, how far away from me are you when you're running by
You're in the same
me?
place.
We're in the same place, essentially.
So you're like literally running
I've never
here.
heard of this paradox.
And you look
right.
up,
It's a little known paradox.
and the
right?
thing
Yeah.
that you see and I see are days apart.
Days apart.
Because of our physical perspective on
Well,
that?
here's what you would think. You would think the light is arriving right now. We should all be receiving this light, but that's not how it works. Motion changes the perception of time.
Did you see how confused Neil looks? That was exactly my reaction too. Like, this can't possibly be true, right? This doesn't make any sense. Then again, relativity has this way of messing with your brain. And when I looked up the Andromeda paradox, it turned out that it originally came from Roger Penrose, who I think understands Einstein's theories better than Einstein himself. So now I wasn't just annoyed at myself for not understanding this paradox, but also embarrassed because I thought I'd read Penrose's books. But let's look at exactly what Penrose said, or rather wrote. This is from his 1989 book, The Emperor's New Mind. Two people pass each other on the street, and according to one of the two people, an Andromedan space fleet has already set off on its journey, while the other, the decision as to whether or not the journey will actually take place has not yet been made. That sounds very similar to what Hakeem says on the podcast, but note that Penrose didn't say that the people who pass each other actually see the event. Penrose goes on, how can there still be some uncertainty as to the outcome of that decision? If to either person the decision has already been made, then surely there cannot be any uncertainty. The launching of the space fleet is an inevitability. In fact, neither of the people can yet know of the launching of the space fleet. They can know only later when telescopic observations from Earth reveal that the fleet is indeed on its way. Then they can hark back to that chance encounter and come to the conclusion that at that time, according to one of them, the decision lay in the uncertain future, while to the other it lay in the certain past. Was there then any uncertainty about that future, or was the future of both people already fixed? What Penrose is going on here is that in Einstein's theory, the notion of now becomes subjective. Neil and Hakeem go on to talk about this in the podcast, but I think they've messed up the relation to the Andromeda paradox. Let me draw this in a space-time diagram because I think this will clarify it. In a space-time diagram, we have space on the horizontal and time on the vertical axis. You have to imagine that this one-dimensional space is actually three-dimensional, and well, good luck with that. If you just stand still, then you move on a vertical line in this diagram like this. If your friend walks by at a slow pace and meets you just when the clock strikes 0, then that'll look like this. Let's say that Andromeda's over here. It doesn't matter exactly at what velocity it moves relative to the two people, so let's just say it doesn't move relative to you. In these diagrams, light travels by definition at a 45-degree angle. You can see immediately that there is exactly one light signal arriving from Andromeda at the place and time the two people meet. So they must agree on what they see. This is why I was so confused by what Hakeem said. It just can't be correct. And indeed, what Penrose talks about in his Andromeda paradox is something else. What these people see is something that happened in the distant past. Andromeda is 2.5 million light years away, so we can only see what happened 2.5 million years ago. Penrose is instead talking about what happens in Andromeda at the moment these people meet. And for this, you have to introduce a notion of now or of simultaneity. You can do this, for example, by saying, well, suppose I place a flashlight left of me at a distance of 100 meters and one right of me at a distance of 100 meters. At which moments do they have to flash so that I see them flashing at the same time? The answer is the flash events both have to be on the same horizontal line. And since I know how far away the flashes took place and how long they traveled, I can figure out which event in my past coincides with these two flashes. So these three events happened at the same moment. And this tells me that generally everything that happens on this horizontal line happens at the same moment. In each moment, everything on a horizontal line is now for me. But here's the thing, your friend who walks by doesn't agree, because between the moment these lights flash and he sees them flash, he's moved. So he sees the flash he's moving towards earlier. But your friend could find out what happens at the same time the same way as you, by putting two flashlights at the same distance from him, and if the flashes arrive at the same time, he'd know they happened simultaneously. The issue is, though, that his idea of simultaneity doesn't agree with yours. His simultaneous surfaces are tilted relative to yours. And so his now doesn't agree with yours. But let's come back to Penrose and the fleet of Andromedans. Suppose the Andromedans want to invade the Milky Way. Here they discuss the idea, and here the fleet takes off. The issue is that as you meet your friend, they're still discussing it in that moment according to you. But according to your friend, they've already left. Now, neither you nor your friend can possibly know anything about this, because the information from Andromeda can't yet have reached you. But this brings up the question of whether the decision was already made. As Penrose writes, was there then any uncertainty about that future, or was the future of both people already fixed? So the Andromeda paradox brings up this question of whether the future is still open or already fixed. The usual conclusion from the relativistic discussion of now is that the future is as fixed as the past. This is what's called the block universe. The only other way to consistently make sense of a now in Einstein's theories is to refuse to talk about what happens now elsewhere. That's logically possible, but it's just not how we use the word now. We talk about things that happen now elsewhere all the time. So I find this an unsatisfactory solution, and I believe that the block universe is correct. I explain the consequences of this in more detail in my book Existential Physics. But to come back to the Star Talk, in the podcast, the two go on to discuss the question of now in Einstein's theories, and that's all well and good. But I think that they didn't correctly explain just what the paradox is. It's not just you. Relativity really is confusing. Even physicists get it sometimes wrong. I find it endlessly fascinating how much physics tells us about the fundamental structure of reality. It's not just relativity, but also quantum physics and generally differential equations and all the maths that we use. If you want to learn more about all of this, I recommend you have a look at the courses on Brilliant. Brilliant offers courses on a large variety of topics in science, computer science, and mathematics. All their courses have interactive visualizations comments and come with follow-up questions. Whether you want to know more about large language models or algebra, want to learn coding in Python, or know how computer memory works, Brilliant has you covered. It's a fast and easy way to learn, and you can do it whenever and wherever you have the time. And they're adding new courses each month. I even have my own course on Brilliant. That's an introduction to quantum mechanics. Actually, code premium subscription.
Toivotan teidät tervetulleeksi tähän Linux-käyttöjärjestelmän.
Tämmöisessä yliopistoympäristössä on se, että niitä kyllä on olemassa PC-koneillekin, mutta niiden hintataso on erittäin korkea. Eli kun esimerkiksi DOS nostaa
Hey everybody, it's Jeff, and today we're looking at a demo of the new Wannix 03 preview. Wannix is primarily a system for building virtual environments that can be run in the browser. You could think of Wannix as a Docker that runs in the browser, though it is a very different approach since it can be used in a number of other ways as well. For example, previous releases explored using it to build a whole new general-purpose computing environment in the browser. We're building it to run developer tooling that otherwise wouldn't run in the browser, allowing us to build a polyglot development environment without cloud servers. That means running everything sandboxed locally in your browser. To be clear, Wannix is plumbing. For now, it will likely only appeal to system builders, tool developers, and those of you interested in a future of malleable local-first software like us. This demo will show some of its capabilities, but at this point you'll still have to imagine specific use cases on your own. And if you are able to, please share potential use cases in the comments for those that might not. That said, let's get into it, starting with some background. The heart of Wannix now is a VFS module, or Virtual File System module. This VFS module is more than just an in-memory file system. It's much closer to the Linux VFS layer. The VFS in Linux is what gives us a single file system view, even though it's made up of several underlying file systems. One might be a partition on the hard drive, one might be held in memory like TempFS, or maybe it's removable media like a USB stick. The Linux VFS is like a router or a switch delegating operations to the underlying file system mounted at a specific path. However, the underlying file system doesn't have to be a storage medium. It could be an API to some system or device. If you've heard of device files, these aren't normal files. They're files representing a way to read or write bytes to a real or virtual device. This goes all the way back to the origin of Unix. The authors of Unix at Bell Labs realized they could use the file system as a user-facing API to their terminal devices, also known as teletypes. This worked particularly well because the protocol to a terminal device was a read-write stream of bytes to display and bytes typed in. This led them to think of the file system more as an abstraction or an API. Encoded in the Unix philosophy, everything is a file. Then, in the late 1980s, the same team at Bell Labs that built Unix created a successor trying to bring deeper compositionality into the design of the system. This successor to Unix was called Plan 9. It took everything as a file to a new level, yielding a system with capabilities we still haven't seen in mainstream operating systems, while being an order of magnitude simpler. In Plan 9, there is no single file system view. Instead, every process has its own file system called a namespace. Child processes inherit namespaces, so by default it feels like a single file system, but you can customize the file system for any individual process. In today's terms, it's the equivalent of every process running in its own container. On top of this, namespaces in Plan 9 are constructed more granularly using file services. File services are assumed to not necessarily be storage volumes, but generic capabilities. There's a file service for getting the mouse position, a file service for drawing to the display, even a file service for working with network sockets. File services could come from the network or from other programs. For example, the Plan 9 windowing system, Rio, is controlled by a file service. Namespaces and file services become primitives for users to build virtual environments with specific capabilities for any process, controlling not only what storage volumes it can use, but what it's allowed to do at all. Even more, you can make a process think it's running somewhere else, or give a process a remote hardware resource without it knowing the difference. So much falls out of this design for free. Even if we have things like Docker and Fuse today, we still can't come close to what could be done with Plan 9. except maybe with WANX. WANX lets you build virtual environments out of namespaces and file services just like Plan 9. And you do this using namespaces and file services. In other words, the file system API is all you need to use WANX or anything built for WANX. Here we are at wanix.run, which is live if you wanted to follow along. This is the debug page, which is an empty page that just includes WANX so that we can manually instantiate it here in DevTools. Now we have a WANX object. And if we look at the API on this object, it's a bunch of familiar file system operations. For example, we can use the read directory method to list the top level or root directory of this VFS. This whole API is async, so we're using this helpers debug option to define slightly more convenient functions to use in DevTools. Await wreaddir becomes just list. So let's use these to poke around a bit. These are all the web-related file services. We'll go into OPFS. And it seems like a lot of people don't know about OPFS, which stands for Origin Private File System. This is a browser storage API like IndexedDB or local storage, except it works like a file system. And there are a couple files I put in here already, which we'll come back to, but for now, let's write a new file using the write file helper. And we can read it back out with the read file helper. Now let's look at file service more like the Plan 9 system API file services. These typically won't let us create files. They work more like the procfs in Linux. Here in CAP, which is short for capability, these two files represent the two big patterns inspired by Plan 9. One is the control file that lets us perform operations specific to the file service, and the other, this directory called new, represents what we would normally call a clone file in Plan 9. These are used to allocate a new resource managed by its own file service. Let's see what kind of capabilities we can create. We'll allocate a pickerfs. This wraps a browser API letting you pick a directory on your system to expose to the page. The caveat being that this is not yet available in all browsers. But we can allocate it by simply reading the pickerfs file, which gives us an ID. Now there's a file service we can look up with this ID. If we read its type file, we can see it is our pickerfs. And now we can finally use the control file to tell it to mount. We just write into the control file a command, and it runs. This pops open the show directory picker dialog, and we'll just pick the WANX source code here. Now the capability has a mount directory containing a read-write mount of the directory we chose. Pretty cool. Now most of what we'll see next are simply variations on the patterns that we've just seen. But then, wait a minute. Maybe this isn't what you imagined when I said virtual environment. Well, it may not seem like it, but this WANX VFS module is a kind of proto-environment, an environment where we can construct virtual environments out of these primitives. What might help us see this as a virtual environment itself is if we had a proper Unix-style shell. So before we see the rest of WANX, let's use the final DevTools helper, boot shell. We'll come back to what boot shell actually did here by the end, but for now, we have a Unix shell. In the shell, we use slightly different commands to do the file operations we were just doing, so I'll quickly demonstrate. We also now have a current working directory, so we can use shorter relative names when referring to files. We have an ls command to list the current directory. We have an echo command, which writes its arguments to standard out, which is normally useless, but in the shell where we can redirect standard out to a file, this becomes the canonical way to write lines to a file. The command cat is used to output files, writing them to standard out, and redirecting with two arrows appends a line to the end of a file. So now file has two lines. And we do have all the other basic shell commands, cd to change directories, makedir, rm, etc. But besides changing and listing directories, most of what we'll be doing is echoing into files to write and catting files out to read. We are in the browser, so of course we have a DOM file service, which means we can use shell commands to inspect the DOM. Using cd to navigate up to web and into DOM, we can see there is already some kind of DOM resource. We can look at its type to see what it is. Xterm, okay. Let's look at its attributes. We can also live manipulate the DOM. For example, appending to this style device file will add CSS to the page. And that's kind of iconic, so we'll leave it. We can make new DOM elements using the clone file pattern from before. In Plan 9, this is called the clone dance, though we've simplified it a bit. And now that we have shell variables and subshells, this is a little nicer. Now we have the iframe resource ID. We can use it to see that, yep, this is an iframe. But of course, where is it? Front-end people will know that we need to add it to the body, which we can do with the body control file. We'll construct a command with echo using the variable. This is what it would look like. Then write it to the body control file. As you can see, we do have some CSS and JavaScript that makes iframes work a little bit like Windows. For now, as a little wink, they intentionally look like Rio windows from Plan 9. We can navigate the iframe by setting the source attribute on it, which we can just write out and send to the iframe attributes file. Since the root of Wanix run loads a shell, this gives us a little shell window. And we can remove the element by sending remove to our iframe control file. As a Unix shell, this is a programmable shell, so we can make some convenience scripts. For example, we can make a domctl where domctl new maybe wraps a operation like this. Let's look at the full source. Plan 9 is full of scripts like this, just wrapping file system operations. All this script does is wrap what we've been doing into a command that feels a little more ergonomic and familiar to use. Considering how few lines this takes, despite being an archaic shell script, I'd call this a worthwhile abstraction. Let's see how this cleans up the clone dance to make a new iframe. Beautiful. Sending control messages is now just the identifier and the command as arguments. As another example, here we'll send a remove command to the iframe. By default, Wanix installs a service worker for the domain. A service worker acts as a proxy for network requests on the page. For example, Wanix uses a service worker to cache itself, allowing Wanix to be used offline. It also uses the service worker to expose the root namespace as if it were served over HTTP. This lets us point iframes to files in our namespace. So if we create a simple HTML file, we can easily view it rendered in a window. In the future, I'd like to explore a file service that lets you fully program the service worker like an HTTP router. We also have a file service and control script for web workers. Web workers let us run some JavaScript in the background. This worker.js file logs to the console on an interval. With a worker.ctl command, we can start this as a web worker. We can see it running from the console, but we can also navigate to the worker and inspect its state. And of course, we could terminate it with the control script or by directly using its control file. Later, we'll see the source code for this file service. One of the most requested features of the last release was to run WASI executables. Previously, Wanix could only run WASM executables built by a custom Go compiler. Now, any language that can compile to WebAssembly and supports WASI can create Wanix executables. Here we have a Zig program compiled to WASI WebAssembly. Look how small it is. But how do we get it into Wanix? We could use the PickerFS capability, but we could also just drag it onto the terminal. This copies it into the OPFS root. And now we can just run it. This program shows its own environment, which is inherited by its parent by default, the shell. Remember, the environment is the file system or namespace the program sees. We could change that environment by manually creating the task and modifying the namespace before starting it. Tasks are the equivalent of processes, and in Wanix, every task has its own namespace. Similar to /proc on Linux, we have a task file service. We can use this to inspect the Zig program we just ran, including its namespace. Let's make a new WASI task based on the last one. We can just copy over the command and environment variables. However, this time we'll remove the top-level cap file service inherited from our root namespace. Starting a task this way effectively runs it in the background, so we can check its exit code to see that it completed. We can see its standard out by reading the appropriate file descriptor. This time, it could only see task and web in its namespace. We can also see this by listing its namespace. So think about this. Since everything in Wanix is done via the file system, not having a part of the file system means you can't use it. File services added to a task namespace give that task its capabilities. That's why we sometimes refer to